Oh, they have to hose down that park at least once per day. When I was on Tatsu, a little kid a couple of seats away from me peed.
Oh!
It's like dripping out of his shoes. I'm like, go to the log ride right now and it's off.
Someone pissed himself?
Yeah, Tatsu, a little kid. Well, that's the way it goes.
That coaster is so fun.
Yo, you're passed out.
Huh?
When we were next to you, passed out.
Did you really? On what?
Viper, I think. It was his first roller coaster ever, and he was like,
That ride is so true.
Yeah, I figured you were
That's such a bad ride.
especially when the grades went
We went on it, and the road is nobody was in line.
Such a bad ride.
I figured that if you push back, then you like flow.
What were your favorite? What were your favorites?
My favorite.
Everybody enjoyed themselves at Magic Mountain?
Yes!
Barf and urine notwithstanding.
yeah. But this was not making it.
I know.
What do you think?
Yeah, it was my last shot too.
I just saw you going left and right, you were like, oh.
And then you hugged me.
Ryan, I assume that's your protractor?
Yeah, I'm trying to get all the tape off.
Okay, also, do you have the washer?
I already put it back.
Okay, yeah, put the washer and the protractor back. And that actually reminds me, since I'm thinking about it right now, there's only one more group that still needs to give me their protractor and washer, Diego's group. So that's Sean, Diego, you got it with you? All right, awesome. Go ahead and take a moment to take it out. Because what I'm doing here, if you'll notice, is I'm crossing off the groups. One of the reasons why I have you sign in as a group is so I can keep track of who still has their protractor and washer. Because then when you give it back to me, and now everybody has, I cross it off. Otherwise, everybody would lose 20 points on their for the Magic Mountain assignment itself, okay? All right, so good. Everybody here in this class has turned it in. You're all ready. You're ready.
I dropped the washer into the trash can last night.
All right, tell you what. Why don't you take your seats? Let's go ahead and get rolling on today. We're going to be doing a lab exercise. So one of the things that you'll do during a lab exercise is fish it out.
Just drop a magnet inside. See
All right, I'll wait till Sean here.
I'll take my seat.
Okay, there you go. Brian, take a seat as well. All right. Before we do get to today's lab exercise, let's go through now the mathematical details of the Doppler effect. If you recall at the end of class last time, I guess that would be on Monday now of this week, I gave you a qualitative description of the two physically distinct types of Doppler effects there are. Okay, the first type is where you have a moving source of sound and a stationary observer. This was the applet that I showed you, and I demonstrated this by using a tuning fork. If a source of sound moves towards you, for example, the wavelength of the sound waves themselves is compressed a little bit. Therefore, if the wavelength is shorter, the frequency is higher and you hear a higher pitched sound. If the tuning fork is moving away from you, then the sound that it emits towards you, the wavelength is kind of stretched out a little bit, so then therefore you hear a lower pitched sound. What we're interested in describing is how do you calculate what is called the Doppler shifted frequency. Now, this is the first of our two different types of Doppler shifts. We have a stationary observer and a moving source. And now, before I begin this derivation, we do, as always, have to define some terms. So a few definitions here to start. Okay, first of all, the speed of sound is just v, 343 meters per second. We are going to measure today, by the way, in our lab exercise. And then the frequency of just the tuning fork itself, that is the frequency that it emits, is just referred to as f. This is the frequency emitted. And what we're interested, however, in determining, what we're interested in determining is called the Doppler shifted frequency. What you actually hear is just called f prime. Doppler shifted frequency. Okay, and then lastly, for the defined terms here, somewhat confusingly, the v sub s, as it's called, is not the speed of sound. This is the speed of the source. Okay, and now for this physical situation, we actually just kind of break it up into two parts. We look to see what happens, first of all, if you have the source of sound moving towards you, and then secondly, if it moves away. And then for those two cases, what we want to calculate is the Doppler shifted frequency in terms of these quantities. Here's how we go about doing that. I'm going to call this here step A. So step A is going to be that the source moves towards the observer. So therefore, think of it like this. Let's say here you are as the observer, like so, and then we have a source of sound. Let's say that the source is right here, and it goes beep. So then therefore a sound wave would propagate outwards towards you, say, like so. Okay, now in the time between beeps, however, our source has moved. It's moved from, say, here to here. Now this right here will be the second position of the source. And it goes beep again, and at this moment then the sound wave would start to propagate outwards towards you in this direction like so. What this then means is that this distance right here is the compressed wavelength that we saw in the applet. Source is moving to the right hand side, beeping as it does. This distance right here is that compressed wavelength that we saw. This is referred to as lambda prime. Compressed wavelength, or shorter wavelength, whichever which way you want to phrase it. Okay, now, however, if the source didn't move, the next time that it would have beeped, it would still be here. So then therefore, propagating outwards from that point would be a sound wave like this. This then means that this distance right here is just the original wavelength, lambda, of the source if it was just sitting there beeping over and over. This distance right here is just lambda. This is the original wavelength. Okay, once again, here's kind of how the process goes. Source starts here, goes beep, sound wave propagates to here. In the time, however, that it takes the sound wave to propagate to here, the source moves from here to here and it goes beep again. So then therefore this distance right here is the compressed wavelength. But if the source didn't move, then this right here would be the original wavelength lambda. Now the only other distance that we need here on this diagram is this distance right here. This is the distance that the source moves in between beeps. That distance is just equal to the speed of the source multiplied by the time between beeps, which is just equal to the period of the sound itself. And now we just add up the distances here. So notice on the diagram that the original lambda down below is equal to lambda prime plus that speed times time term. You end up with this. Like so. And now what we do is just convert this little distance equation into a description of speeds and frequencies. Okay, here's how that's done. Okay, right here is the original wavelength lambda once again. This is equal to the speed of sound v divided by the original frequency that's actually emitted. Okay, then here, next, is the compressed wavelength lambda prime. This is equal to the same speed of sound, but now divided by what we're trying to find, which is the Doppler shifted frequency. Okay, and then lastly, this speed of the source times time. This time here is the period. The period, however, is just the inverse of the original frequency of the sound itself. Like so. And then all that we do here is just solve for f prime. And I'll spare you the algebra. But when you do solve for f prime, you end up with the following little expression. The Doppler shifted frequency ends up being the following quantity. So that's what happens when you run through the algebra there and solve for f prime. You eventually end up with this expression here. Now here's how the little expression works. Notice that the denominator of the expression is a number that's smaller than the numerator. So then therefore, in parentheses, you end up with a number that's greater than 1. This then means that f prime is greater than f. So you hear a higher pitched sound when the source is moving towards you. Notice also, however, that this equation doesn't work if the speed of the source is equal to the speed of sound or greater. Because if the speed of the source is equal to the speed of the sound, you end up with 0 here in the denominator, and then therefore f prime is undefined. If the speed of the source is greater than the speed of sound, then you end up with a negative number, which makes no sense in this context. So in other words, something else has to happen if the source is moving at the speed of sound or greater. We'll get to that a little bit later on. But for now, this expression here only works if the speed of the source is less than the speed of sound. Okay, now situation B, I'll call it, is just a little bit backwards of what I did here, but in situation B, we'll have the source move away from the observer instead. When we do this, a couple of the terms here in this expression just kind of switch around a little bit. You basically end up with this. So now situation B, source moves away from the observer. And that situation then kind of gets laid out the following way. So once again, here's the observer like so. Let's say that the source starts here, it goes beep, and the sound wave propagates towards the person, say, like so. Okay, the next time, however, that the source goes beep, it's moved to the left-hand side somewhere in my diagram. It's right here. So this right here is the second position in this little description of the source. It goes beep, and the sound wave then begins to propagate towards the person. So right here is that stretched out wavelength that we saw in the applet. This is the lambda prime behind the source. So right here is lambda prime. This is the longer or stretched out wavelength. So, however, if the source didn't move, the next time that it goes beep, it would just still be right there, and that sound wave would then propagate towards the person. In other words, it's then therefore this distance here, that's just the original wavelength lambda, if the source wasn't moving, like on the top board. Okay, and then lastly for this little description, the only other distance that we need is the distance that the source moves in between beeps. So the distance that the source moves in between beeps is equal to the speed of the source multiplied by the time between beeps, which is just the period of the sound itself. And now we just add things together. Notice it's just a little bit backwards of the equation that I have above. In this case, it's lambda prime is equal to lambda plus VST, like so. Okay, and then, like I did in that step there above, what we do is we change these distances to speeds over frequencies. So this right here, lambda prime, is the speed of sound divided by the Doppler shifted frequency, f prime. And the original wavelength lambda is the speed of sound divided by just the frequency that's emitted. And then in the last term, we once again write the period as just the inverse of the frequency itself, like so. And then you take this expression here and just solve it for f prime. When you solve it for f prime, you end up with something that looks very similar to this expression here. When you solve for f prime, you obtain the following. You end up with a plus sign in the denominator instead. So notice how this works mathematically. The numerator of the expression is less than the denominator. This then means that f prime is going to be less than f. So you're going to hear a lower pitched sound. Nothing weird happens if the speed of the source is equal to the speed of sound or greater. You just end up with a really low frequency. So it doesn't matter what the speed of the source is in this context. If you're behind it and it's moving away from you, you're just going to hear a lower pitched sound. Now these two expressions here are actually combined together into one equation. They're combined together into the following expression. Like so. And the way that we read this equation is that the top symbol in the denominator, that's the first situation that we looked at, that's when the source moves towards the observer. The bottom symbol in the denominator, the plus sign, that was our second situation. That was when the source moves away from the observer. There's an easy way to remember this. Top means towards. T for top, T for towards, top means towards. So the negative sign is towards, the positive sign, the bottom symbol, is away. Okay, now that's the first physical type of Doppler shift. There is, however, a slightly different second type. And this is where you have a stationary source of sound, but now a moving observer. So imagine having a siren and you start running towards it. If you start running towards it, you're going to see the speed of sound from Galilean relativity as greater than 343 meters per second. So then therefore you're going to hear a higher pitched sound for that reason. If you ran away from the source, then you're going to measure the speed of sound as less than 343 meters per second. Therefore you're going to hear a lower pitched sound. So when we calculate the Doppler shifted frequency in that situation, either you running towards or running away from the stationary source, then we, instead of adding up distances as we did here in these diagrams, we instead add up velocities using Galilean relativity. Here's how that's done. So I'll call this then situation 2, and I'll break it up once again into 2 parts. I'll call the parts here C and D for clarity. Okay, and now for situation 2, now we're going to have a stationary source and a moving observer. We then therefore need one more defined term, and this describes the speed of the observer relative to the ground. The observer has a speed that's just called VO. That's not a V naught, it's VO for observer. So that's how that person moves relative to the ground. Excuse me. Okay, now, once again, there's 2 situations here. They're just slightly backwards of each other. Okay, first of all, I'll call it part C. Let's say we say that the observer moves towards the source. So then we would have to picture it like this. Okay, here's the stationary source of sound. We'll say that the sound waves will propagate to the right-hand side, and then the observer is here. The observer moves in this direction like so, with speed VO. You know, as I mentioned, this is a Galilean relativity situation. So we have to go all the way back to the good old days of chapter 3. Remember the velocity transformation equation? Yes, I knew that the groans would begin as soon as I wrote it down. Don't worry, there's not going to be any I hats or J hats or anything like that in this problem. It's just one-dimensional, so just plus signs and minus signs. But if you remember, we have to define everything correctly when using Galilean relativity. Okay, first of all, as is always the case, we treat the stationary reference frame as the ground. The moving reference frame, which if you remember, by the way, is called O prime, is going to be the observer. And then lastly, we would have the object. The object is not the source. The object is the sound wave. And now here's how we add up our velocities. Okay, first of all, we have here the velocity of the object, the sound, relative to the ground. This is just the speed of sound V, 343 meters per second. Okay, then we have essentially what we're trying to find here, the velocity of the sound relative to the observer. That's the V prime. I'll just leave it like that. And then lastly, the U vector, if you remember, is the velocity of O prime with respect to O. That's the velocity of the observer with respect to the ground. That's just the VO. Points, however, to the left on my diagram, therefore I'll give it a negative sign myself. So that's what happens when we just add up the velocities. And then what we need to do is write this expression in terms of the original frequency that's emitted here by the source. In order to do that, we have to adjust this term right here, the speed of the sound as seen by the observer. What we do is we write that term as wavelength times frequency, where the frequency is what we're trying to find in this process, and that's f prime, the Doppler shifted frequency. Then after that, there's just one more step. How do I turn this expression into something involving the original frequency that's actually emitted by the source? That has to do with the original wavelength lambda. What we do is we write the original wavelength lambda as the speed of sound v divided by the original frequency. Like so. Now what you do is you take this expression here and then solve that for f prime. And once again, I'll spare you the algebra. But in situation C here, when you do solve for f prime, you end up with the following expression. you end up with this expression here. Okay, notice it's distinctly different from the equations that I still have on the bottom half of this board. But now in the numerator of that expression, you end up with a number that's greater than the denominator. So then therefore f prime, the Doppler shifted frequency, will be higher pitched than the original f. So if you run towards the source, you're going to hear a higher pitched sound, like so. Okay, then the last situation is actually very short at this point, very simple. What happens if the observer moves away from the source? Well, if the observer moves away from the source, all that we do is we just turn around the VO and point it to the right-hand side. This then just turns into a positive sign in the Galilean relativity equation. So the last part of the process here is very simple at this point. We're just briefly writing it out. It would just look like this. So now this is lastly here, part D. Okay, part D of the problem here, the observer will move away from the source. And by the way, we're going to assume that he's moving slower than the speed of sound. The observer moves away from the source. So then therefore we just turn the VO and point it to the right-hand side, like this. Okay, by redirecting that velocity vector in my velocity transform equation here, the only thing that changes is that the negative sign now just becomes a plus sign. Like so once again, we're just adding up velocities here using Galilean relativity. We run through the exact same derivation, except now we have this plus sign, and then we solve for f prime. When you solve for f prime for this last situation here, situation D, you end up with this. You end up with that expression there. So with that expression, that last one for part D, notice that the numerator of the expression is less than the denominator. So then therefore the Doppler shifted frequency f prime is going to be less than the original frequency f. So if you run away from a source of sound, you're going to hear a lower pitched sound. Okay, notice that the equation doesn't work if the speed of the observer is equal to the speed of sound or greater. So it makes no sense, in other words, in that context. We're just assuming that the observer is moving at a speed that is slower than the speed of sound itself. Okay, like the bottom two expressions, these guys here can be combined into one equation as well. When you combine these guys into one equation, you just end up with this. Like so. And the reason why I wrote that expression the way I did is because we read the symbols exactly the same way as I did for this bottom expression. The top symbol always means towards. So if the observer moves towards the source, the top symbol here in the numerator is the plus sign. The bottom symbol always means away. So then therefore if the observer runs away from the source, like part D of the problem we just did here, then therefore it's the bottom symbol, it's the minus sign. So we write the symbols here in the two sets of expressions like this for that reason, to be consistent. It turns out, however, that what I've spent the better part of the last 20 minutes doing is leading us to a point where you actually just end up with one equation. One equation which describes every possibility. Because you can think of the problem now in the following way. Ask the following question. What would happen if both the source and the observer were moving? If you ask it that way, what you end up with is just one expression. One expression that takes care of every possibility.
That's what I need.
So if you're Lord of the Rings fans, it's one equation to rule them all.
One ring to bind them.
So think of it like this. What happens if both the source and the observer were moving? The easiest way to think of this is kind of like as a two-step process. So imagine, first of all, that you're the observer and you're standing still, and then the source is moving. It's either moving towards you or away from you. So then therefore you would hear a Doppler shifted frequency depending upon which way the source was moving relative to you. However, if you start moving, then this Doppler shifted frequency is going to get shifted again, because then you would have the observer, for example, moving with respect to the ground. You would end up with a second Doppler shift. So think of it as a two-step process. You're initially stationary, you listen to a moving source of sound, you hear this. However, if you start moving, this guy gets Doppler shifted, such that you then hear this. So what I'm going to do is just simply take this expression here, plug it into there, and watch what happens when I do it. I'm going to do this expression. Like so, and notice that it simplifies. Notice that the V's here and here get swapped. And we're then left with the following expression. This is the one equation to rule them all. You end up with this expression here. This expression here takes care of every possibility, and we read the symbols always the same way. Top symbol means towards, T for towards. The bottom symbol means away. So for example, if the source moves towards the observer, it's the negative sign. If the observer moves towards the source, it's the positive sign. However, if everybody's moving away, if the source moves away, it's the plus sign. If the observer moves away, it's the minus sign. So the top symbol always means towards, and the bottom symbol also means away. It also takes care of just the two sets of original expressions by themselves in the following way. For example, if the observer was stationary, VO is equal to 0. Here's our first set of expressions, like so. If the source was stationary, so VS is equal to 0, that's our second set of expressions, like so. So it takes care of all of the bases. Now, it took me the better part of 25 minutes, half an hour or so, to derive this expression here for us in class. A little tricky to do, but it turns out that using the expression is really easy. There's nothing to it. So let's take a look at one example. So what we'll have is a car with a siren attached. That's obviously the source. The source relative to the ground is moving at a speed of 10 meters per second. Okay, then we have an observer moving relative to the ground at 2 meters per second, and the siren emits a frequency of 600 hertz. What we want to calculate are the Doppler shifted frequencies for the 4 possibilities that are present in this example. Griffin. Okay, so here's what we have. Okay, first of all, let me just place our basic expression up here. We'll just refer to it as we go. Okay, now in the example, first of all, the speed of sound V is just 343 meters per second. Speed of the source is 10 meters per second. Speed of the observer is 2 meters per second. And the frequency of the siren is 600 hertz. So here are all the values. Okay, now what I'm going to do is take care of the easier of the 4 situations first. Let's just describe what happens if they go like this, and then let's describe what happens if they go like that. Those are simple and straightforward. As we'll see, however, a little bit later on, if they're doing this or this, it's not quite the same thing. You know, you'll see what I mean when I get there. But first of all, we'll call it part A. What we'll do is we'll take the source and we'll move like so. Where VS is given as 10 meters per second, And then we'll have the observer, have them go like so, or the VO. So I'm just going to do it like this here first. The easiest way to approach the equation is just to look at the directions associated with each object and then therefore treat the numerator and denominator of the expression separately. So first of all, the denominator. We have the source obviously moving away from the observer. So the bottom symbol means away, therefore it's the plus sign in the denominator, like so. Okay, now we have the numerator, which has to do with the observer. Obviously its observer moves away, so it's the bottom symbol in the numerator, which is the minus sign. Like so. And now we just fill in all of our terms and calculate this out. So what I end up with now is 343 minus 2 in the numerator, which is 341. And then divided by 343 plus 10, which is 353, multiply that then by 600 hertz. And this Doppler shifted frequency is quite low, 579.6 hertz. That's what the observer hears. Okay, the second easy situation is what happens if they just do this. So in the second situation, just to picture it, we have the source like so, going like this, and then the observer like so, going like that. Okay, once again, when you approach the equation, you just look at the directions and then just get the symbols right. So first of all, the denominator of the expression, which is the source. This is obviously source moves towards, T for towards, therefore it's the top symbol. It's the minus sign in the denominator. So, okay, then for the observer, that's the numerator of the expression. Obviously its observer moves towards, so it's the top symbol in the numerator, which is the plus sign. Like so, and then we just fill in. So numerator of the expression is 343 plus 2, that's 345. And divided by a total of 333 here in the denominator. Multiply by 600 hertz, then we end up with something rather large, 621.6 hertz. Like so. Okay, these first two situations here are pretty simple and straightforward. What could be initially a little bit tricky is what happens in the other two situations, that is, say like this. So let's say we take the source and go like this, and then we take the observer and do this. Okay, now just qualitatively, let's think about how this is going to have to work. Okay, remember that the siren, the source, is moving at a speed of 10 meters per second, and the observer is only moving at a speed of 2 meters per second. So the siren is going to catch up with the person. If you think of me as the observer and the marker here is the siren, it basically looks something like this. So then therefore, am I going to hear a higher pitched or lower pitched sound than 600 hertz? It will be higher pitched. So let's see what happens. So once again, we just set up our expression and start to plug in. Okay, first of all, we have the denominator. It's obviously the source moving towards the observer. So therefore, we use the top symbol in the expression. That's the minus sign. Now, be a little bit careful here. Yeah, the source is catching up with the observer. But would you still think of this as observer moves away or observer moves towards? Away. Okay, I'm running away from the marker even though it's catching up with me. So then therefore its observer moves away. Away is the bottom symbol, then therefore is the minus sign in the numerator, like so. And then you just fill in the terms. Okay, when you fill in the numbers, by the way, you always just plug them in as positive numbers because all of the directions have been taken care of in deriving all of this to begin with. So then therefore, we have, first of all, 341, and then divided by 333, multiply all that then by 600, and you end up with a higher pitched sound than 600 hertz, but it's not quite as high as this situation here from earlier. This is about 614 and change. Like so. Okay, and then the last situation is not the same as this. In the last situation, we have the source like so, and the observer like so. As we'll see, it's not the same situation as what I drew directly above. Because now you got to think of it like this. I'm the observer, here's the source. Remember, the source moves faster relative to the ground than I do. Therefore, the situation kind of looks like this. Like so. So therefore, am I going to hear a lower pitched or higher pitched sound than 600 hertz? Should be lower. So let's see what happens. So set up our expression. Okay, once again, let's do the denominator here first, which has to do with the source. Obviously, the source is moving away from the observer. So if source moves away, in the denominator of the expression above, it's the plus sign, the bottom symbol, like so. Okay, now be a little bit careful there. Okay, yeah, the siren is outrunning the person, but would you describe this as person, the observer, moves towards or away? Yeah, I'm still running towards the marker, even though it's outpacing me. So then therefore, I'm still moving towards it in that sense. Therefore, we still use then T for towards. We use in the numerator of the expression, the top symbol, which is the plus sign. And then just fill in. So numerator is going to be 345, and then divided by 353 in the denominator, multiplied by 600. And you get something lower pitched than 600 hertz, but not quite as low pitched as situation 1. This is about 586 and 4 hertz. Like so. So as we saw, deriving the Brown expression there at the top board was a little tricky to do, but using it is terrific. There's nothing to it. You just got to make sure that you get the directions.
Do we have to derive the equation?
No, you just got to know how to use it. Okay, and it's easy to do, as you can see. All right, let me erase, and then let's go ahead and get to today's lab exercises before Lena falls asleep completely.
Yeah, Lena.
That's asleep.
Mr. Shaw, do you have tissues up there by any chance?
Sorry, I don't. I do have paper towels, though. Getting tissue is kind of low on my priority list, I need to say it.
I'll get a bit of
All right, let me erase this junk. Let's go ahead and now get to today's lab. Speed of sound. Okay, this is going to turn into a formal lab report worth 35 points. It is, however, a pretty short lab, but it is due next time. Today being Thursday, next time is, it's today being Friday. Is today Friday or Thursday? It's Friday, God. Well,
Shut up, the weekend, right now.
I know. It's due Tuesday of next week, that's the 21st. And by the way, it is your last formal lab report. There are some mini labs to still do, but this is the last formal lab report. All right, now, the purpose here, very simply, is to measure the speed of sound. And the theory behind this exercise is very simple, so then therefore I'm just going to describe it already in the context of the procedure. What we're going to do here is we're going to use a closed pipe. It's exactly the demonstration that I showed you prior to our Magic Mountain trip. I'll re-show it to you here once again in just a few minutes. But remember what I do in this demonstration. What you're going to do is you're going to take a graduated cylinder and you're going to fill it up almost to the top with water, leave maybe an inch or two like so. So right here is the water line. And then what you'll do is you'll take the metal cylinder and you're going to immerse it into the water like so. Okay, now when you do this, as you've seen, there is a ruler that is taped to the side. Make sure that you have the origin of the ruler at the top like so, such that when you do immerse it into the water, we're going to measure then directly the distance L to the water line like this, which is then just read directly off the ruler. So before I get to the description of how we actually go about doing this, just make sure that the origin of the ruler is at the top. Okay, then what you do is you take a tuning fork of known frequency F. All of the frequencies are printed on the forks themselves. And you then, moving the metal tube up and down, position it such that you hear the N equals a 0 antinode. Now, as you'll discover, there's going to be a little bit of a learning curve associated with doing this, because it's assuming you've never done it before. So how do you go about doing all of this? Okay, well, first of all, take one of the cups, by the way, and fill it up with water. You're not going to be able to fit the graduated cylinders themselves underneath the faucet. And then fill up the graduated cylinder almost to the top. Leave an inch or two, say, like so. That's good enough. Then, making sure here that the origin on the ruler is up here at the top. Take the tuning fork, give it a good whack. Then position it such that you hear then right here the n equals 0 antinode. Now the distance from here to here, the water line, that's the distance that we need to measure by using the ruler. That's going to be our distance L. That's right here on my diagram. The rulers are in terms of centimeters, but you make the measurement and convert it then into meters by dividing by 100. Now here's the little bit of theory that we do have in play in this problem. Remember that the fundamental frequency associated with a closed pipe is the quantity V over 4L. So then basically, very simply, if you know what the frequency of your fork is, and you measure the distance L, the only thing that's unknown here is then therefore the speed of sound V. So that's kind of the basic idea. But what you'll do here is you're going to make this measurement of L for 5 different forks, 5 different values of frequency. So measure L in terms of meters for 5 different forks. In other words, 5 different frequencies F. And then you start to tabulate your data in the following way. You're going to have 3 columns to your data table. The first column is going to be frequency in hertz. Second column is the length L of the closed pipe in terms of meters. And then in the last column, I want you to make a calculation. I want you to calculate 1 over the quantity 4 times L. Not 1/4 of L, but 1 over 4 times L. Use parentheses on your calculator to do this carefully. The units, by the way, will be 1 over distance. It's meters to the -1. The reason why I'm having you calculate this in the last column is because if we then graph the frequency F versus the quantity 1 over 4L, we're going to get a straight line where the slope of the line is equal to the speed of sound. Yeah.
Just out of curiosity, when you did the tuning fork or whatever, and you stick it over the thing,
I'll do it again for you.
does each one have, like, does every tuning fork have a specific L?
Yeah, it's going to have a specific L. And there's a couple of things I also want to mention about doing this. As I said, there is a little bit of a learning curve here. So here's a few things you want to watch out for. You want to ignore the high-pitched sound when I give this a whack, like so. If you're not sure what the sound should be with the fork, take the stem of the fork and just press it to the desk like so. And you can then hear the sound a little more clearly. So if you're not sure which sound you should be looking for, you can do that little test. Okay, and then after you do give this a whack and then position it like so, make sure once again that the origin is here at the top. Okay, you can overshoot it very easily as I just did. Basically until you get the loudest tone. And hold the fork exactly as I'm doing here, like so, right at the edge. If you hold it like this as opposed to like this gives you a softer sound. So hold it like this. If, by the way, you're not sure if you're hearing this correctly, you can kind of cheat it a little bit. Here's what I mean. Okay, here's our expression. What you can do ahead of time, if you're not sure if you're hearing the n equals 0 antinode correctly, is just calculate what the L should be if the speed of sound is 343 meters per second. In other words, L is going to be V over 4 times F. If you wish, go ahead and calculate what the L should be ahead of time to help you find it if you're not being successful in doing so. So if you do it this way, are you kind of using the answer to help you get the answer? Yeah, sort of, but that's okay. It's just because you're a little bit inexperienced. So if you're not sure if you're hearing it right, just calculate what it should be ahead of time, and that'll help you do it, okay? Okay, once you have that data then, as I just mentioned, you construct the following graph. You plot frequency in hertz versus the quantity 1 over 4 times L here, like so, on a horizontal axis. When you construct this graph, you'll draw a best fit line with your points the slope of the line here is equal to the speed of sound, v. Now, it should be equal to, in theory, 343 meters per second. So then therefore, the last step here is to just calculate a percent error between your slope and what it should be, which is 343. If you do this carefully, if you're right on the antinode and you've got the measurement accurate, you should get a really good result. A couple of the groups over the last 2 days here were getting results of less than 5% error, and that's a pretty good result by doing this exercise. All right, let me show you where everything is. I do have some graph paper, by the way, and rulers, of course, as is always the case here at my desk. But then everything else is essentially here in the back of the room, as it always is. Okay, first of all, there's some cups here such that you could fill up the graduated cylinders with water. Right here are the metal cylinders. Once again, make sure that you have the origin of the metal cylinder at the top. Okay, here are all the tuning forks. I don't really have enough for each group to grab 5 forks all at once, so I have to kind of share them around a little bit. Some of the forks are pretty thin. These little guys right here, they work just fine, but they give you a really soft sound. So then therefore, when you're making measurements, make sure that you're kind of quiet here in the room, such that you can hear your own n=0 antinode and everybody else around you. So there's no need to shout at your lab partner when your lab partner is sitting right next to you. So just keep your voices down. Okay, right here are the graduated cylinders just lying on their sides. Be careful with these guys. They're Pyrex. They'll break. Try to keep this always in the center of your desk. Be aware of where it is at all times. Don't place it at the edge of the desk and go, what? And knock it over and break it, because then you're going to owe me some money. So please be careful with these guys. Okay? All right, are there any questions? Shouldn't take us that long, actually, to end up with a final result, maybe about a half an hour or so. Okay, go ahead and begin.
Yeah, okay. Come on, we're gonna do that left side there.
Yeah, he changed his mind.